Okay, so example 1. A student collects nitrogen gas in a flexible container. The gas occupies a volume of 75 liters. The pressure is 1.2. Pressure's changed to 2.4 with no change in the temperature. So there's our no change in temperature, okay? So that means think of the ideal, or not the ideal gas, we'll get there. The combined gas law, and take out the temperature. You take out the temperature, what do you get? You get P1 V1 equals P2 V2, okay? And with that equation right there, we can now solve for the answer. So the initial pressure is 1.2 atmospheres. The initial volume is 75 liters. The final pressure is 2.4 atmospheres. And again, even though you could probably do this without showing your work, always show your work. Okay, and then our final volume is what they want to know. I'm going to divide both sides by 2.4 atmospheres, 2.4 atmospheres. Atmospheres cancel. 1.2 times 2.4 times 75 equals 37.5 on a calculator. Every single one of these numbers has two significant figures, so my final answer would be 38 liters. Okay. Example 2, a student collects nitrogen gas in a flexible container. So it's flexible, that means the volume can change. Okay. No change in the pressure. So again, think of the combined gas law. Take out pressure, and you've got V1 over T1 equals V2 over T2. Okay, so the initial volume, and again, wait a minute, they give us the pressure right here. Why do they do that? Just to mess with you. Okay, but they say there's no change in the pressure. So even though they give us the pressure, it might come up later in it, like if there was a part A and a part B, it might come up later, but for this specific question, we don't use that pressure. So just because they give it to you doesn't mean you're going to use it. You got to be able to realize that oh, wait a minute, they give me the pressure, but they say no change in pressure, so I don't need to use that. So the initial volume 1.2 atm. Oh no, that's the pressure. Holy cow, I'm struggling today. Initial volume 75 liters. Okay, and the temperature is 25 degrees Celsius, so immediately change that to 298, so 298 Kelvin. The final volume is what they're asking us for, and then the final temperature is, again, 273 plus 50 is 323 Kelvin. Okay, and now to get V2 by itself, I'm going to cross multiply, and I'm going to divide. So that makes it 75 liters times 323 Kelvin. I cross multiplied and I move that 323 up there. I do the same thing. I move the 298 Kelvin over here times V2. And then to get V2 by itself, I'm going to divide both sides by 298. Okay, and then I get my answer, which will be in liters because, as we can see, the kelvins there are both going to cancel. So 75 times 323 divided by 298 should be a little bit bigger than 75, which it is. Two significant figures in 75, so that is 81 liters. Okay, example 3. A student claims that the pressure of a gas increases at constant volume when the temperature increases because the gas becomes more dense at a higher temperature. Do you agree or disagree with the student? I'm going to say right away, I'm going to answer the question. I'm going to go ahead and disagree with the student. And then I'm going to explain why. Why is it that the pressure of a gas, when the volume's constant, why does the pressure go up when the temperature increases? I'm going to disagree because a gas at a higher temp will have greater, what's the first thing we said? Kinetic energy, and will hit the walls more often and with more force, which, and I'll just kind of summarize here, which, and what happened, the pressure went up, which increases the pressure. Okay, so I'm saying I disagree because here's why it happens. Okay, I don't want to say anything about, I don't really know. I don't know, does the density change much? It might change a little bit, but it shouldn't, because if it's in a confined space, density is mass over volume. Again, you're at a constant volume, so that doesn't change. The mass doesn't change. But again, I want to tell the grader or the person grading this question, this is why the pressure does increase when the temperature goes up. Okay? So I'm sure you could have used, there's multiple ways you could have answered. You could have talked about how since the volume doesn't change and you haven't changed any amount of the gas, the mass isn't going to change, so therefore the density isn't going to change. So if you said disagree and then talked about that, I'm sure you would get the point. But what they're wanting you to do is they want you to tell them why. Okay, if it isn't because of the density, then tell me why. Okay, example number 4. Give 2 reasons why a balloon gets smaller when the temperature of the gas inside the balloon is decreased. So when the temperature is decreased, then we know that the kinetic energy decreases. Okay, so that's one thing you could say. Another you could say is that when the kinetic energy decreases, the particles are moving slower. And you could also say particles hit, this is really what I'm looking for when I say the 2, hit the walls of the container less often and with less force. Those are really the 2 that I was looking for. How did we get to there? Because kinetic energy goes down, the particles are moving slower. So if they're moving slower, they're hitting the walls of the container not as often. And when they do hit the container, they're not hitting them with as much force. Okay, example 5. If an equal amount of 2 gases, CO2 and O3, is confined in a closed vessel at constant temperature, which gas, if any, has the greatest pressure? So here's where we're starting to have to think a little bit here. Okay, we've got an equal amount of the 2 gases. Okay, CO2 and ozone. They're confined in a closed vessel, so the volume's the same, the temperature is the same. Which gas, if any, has the greatest pressure? And the amounts of the gases are also equal to each other. Okay, so, and this may be more of not a combined gas law, an ideal gas equation question. But if you've got pressure, and yeah, I think this is probably better solved. I'm just trying to think here. How we would know it has the greatest pressure. Because, again, if the volumes are the same, the temperatures are the same, using the combined gas law, if everything is the same for 2 of the variables, P2, V2 over T2, and this really should be using that ideal gas equation because we have to consider how much of each gas we have. But in this case, because the amounts are equal, if these 2 things are constant for both of them, if they're the same, then the pressures have to be the same as well, unless, again, you have more of one gas or the other. Okay, so which gas, if any, has the greater pressure? I would say they both have the same pressure. Okay, because constant volume, constant temperature, pressures must be the same when the amounts are the same. Okay, example number 6. So here's, we talked about this earlier about when the temperature goes up. If it goes from 75 degrees to 300 degrees, how much does the pressure go up by? So this is kind of a Gay-Lussac's law. P1 over T1 equals P2 over T2. Okay, but it just says a known quantity. We don't know the pressure. Okay, but they're asking about pressure. So really, what's the pressure going to do? It's, again, the key is, well, it might go up by a factor of 4 because the temperature goes up by a factor of 4. In Celsius, it does, and you can't use Celsius. So how much does it go up? Well, it goes up from 348 Kelvin, that's 75 degrees Celsius in Kelvin, and 573 Kelvin. There's your 300 in Kelvin. So how much does it go up by? A ratio of 573 to 348. C is the correct response. Okay, and then our last one for today. So you've got a balloon, it goes up into the air. Which of the following explains what happens to the volume of the balloon as it rises from ground level to an altitude where the air temperature is 220? So the temperature is going from 273 down to 220. It's going down a fair amount, but the pressure is going from 1 atmosphere all the way down to 0.1 atmospheres. It's going down 10 times. Where the temperature, yes, is going down a little bit, but the pressure is really what's is changing here much more dramatically than the temperature is. So think about the combined gas law all put together here, that they're asking us about the volume of the balloon. So temperature does go down a little bit. So from T1 to T2 it does go down a little bit, but the pressure goes down again by a factor of 10. Okay, so if we can even put the numbers in, we can say 1 ATM, and they don't give us the volume, so I'm just going to say V1 over, and then the temperature starts at 273 equals the final pressure is 0.1 V2 over 220. Okay, so the ratio, and so we can solve this for the ratio of V2 over, and really I'm probably overcomplicating this. If you understand, okay, that when the pressure goes down, forget temperature altogether. When the pressure goes down, what's the volume going to do? The volume is going to go up, okay? The volume is going to go up by almost 10 times. Because of that decrease in pressure, the pressure goes down by 10, the volume is going to go up by 10. Now, the volume is going to go back down because of that drop in temperature, but not as much as it expanded due to the increase in the pressure. So that's typically why a balloon will eventually pop when it gets into the atmosphere, is because that the pressure outside is so low that pressure from the inside becomes so great that the balloon will eventually pop. Okay, so the volume will increase. The volume will remain unchanged because of the counteracting effects. True if they were the same ratio, but again, the pressure is going down way much more than the temperature is. So B is a no. The volume will decrease. Nope, the volume is going to get bigger. It cannot be determined. Yes, it can. Okay. The volume will decrease because the decrease in air pressure will have a greater effect than the decrease in the temperature. That is true. Okay. And you can't look at the number. You can't look at, well, it's only going down by 0.9. You have to look at it's going down by a factor of almost 10, whereas the temperature is going down nowhere near that much. So A is the correct response. Okay, that's it for the combined gas law.